Hello everyone, in this video we're going to talk about SP mixing and how it affects molecular orbital diagrams. To understand SP mixing properly, we first need to look at how we predict MO energy level diagrams. So we'll start by predicting MO energy level diagrams for B2, C2 and N2 using the standard orbital ordering that we normally apply to O2 and F2. So after drawing the MO diagram for B2 using the standard ordering, we can calculate that the homosymmetry is sigma, magnetism is diamagnetic. So both of these predictions are actually incorrect when compared to experimental data. Moving on to C2, the standard ordering gives a homosymmetry pi, magnetism paramagnetic. Here, the magnetism prediction is wrong. Experimentally, C2 is diamagnetic. And lastly, N2. So using the standard ordering, we got homosymmetry pi, magnetism diamagnetic. This time the magnetism is correct, but the homosymmetry is wrong according to the experimental values. We should have sigma. So comparing these predictions with experimental results, we can clearly see that something in our MO level ordering is incorrect. So the question is, what changed to give the experimental values? To fix the ordering, we're going to try and flip the position of the sigma 2pz relative to pi 2px and pi 2py, so that the pi orbitals lie below the sigma orbital. Once we do that, we can fill the MO diagrams again. Here we have the diagrams filled. I just want to highlight that we have flipped the 2px 2py relative to the 2pz. So after the flip, our predictions for bond order, homosymmetry, and magnetism will all match the experimental values. So this quote-unquote fix actually works. It's also important to know that the 2px, 2py have different energy compared to the 2pz, and the p subshell contains 3 degenerate orbitals, and then when forming the molecular orbital, we split them into pi and sigma, which have different energies. Inside of the pi, we have 2 different orbitals, which are still degenerate. So this splitting creates the corrected ordering that matches the experimental behavior. So why does sigma 2pz sit above pi 2p only in lighter diatomics? This behavior happens only in lighter diatomic molecules because of SP mixing, which is also known as sigma 2s sigma 2pz interaction. And here is why. So in lighter diatomics, the 2s and 2p atomic orbitals are closer in energy and have compatible symmetry along in the internuclear axis. Because their energies are similar, the bonding sigma 2s and sigma 2pz molecular orbitals can mix. This mixing gives both orbitals a combination of s and p character. If you look at the small energy diagram on the slide, the 2s and 2p levels for lighter atoms sit closer together, which allows that crossover. As the atoms get heavier, the separation between 2s and 2p increases, and the mixing disappears. When the energy difference is larger than about 1 electron volts, mixing does not occur. So the sigma pi ordering in lighter diatomics is a direct result of SP mixing. Also remember that the 2pz forms sigma bonds, while the 2px and 2py form pi bonds. This is why the sigma 2pz is the orbital involved in the mixing. This diagram shows where the flipping occurs. So for O2, F2, and Ne2, we see the normal standard ordering, but starting at N2 and lighter, the sigma 2pz orbital is pushed above the pi 2p orbitals because of SP mixing. This causes sigma 2p to shift upward in energy and pi 2p to shift downward. And importantly, this mixing only affects bonding molecular orbitals and it does not happen in antibonding. And that's everything for this video. I hope this helped make SP mixing and MO energy ordering a bit clearer. Thank you for watching.